All right, so I didn't create a formal presentation, but just to orient people, this is what we're currently doing for ICP-MS data for data reduction. So this is, I'm not going over right now how to export data. We're starting from the point at which you've already done some initial quality control checking. And when I say initial quality control checking, what that means is you've looked at a number of the calibration curves. You've made sure they're kind of linear and look reasonable, that you've also looked at our internal standard. We'll talk quite a bit more about that, and that we have good internal standard recovery, and that you've looked at the check standards and they seem to be reproducing somewhat accurately and precisely. And typically I'm doing this relatively briefly, but it's useful to do that before you download, because otherwise you get somewhere else and are starting to work on the file and you realize like, oh no, everything is crap. So the way this is organized is it downloads, and I always save it as an XLSX so that I can work with it in an Excel, because the type of spreadsheet it saves in is not always compatible with all computers. So what it's got here in this top line is it's going to tell you what each column is. And let me do some wrap text so you can see. So this is the sample list. This is the run number. This is the sample name. And we have set up the export file to record certain information that we're going to use. It's important to know we don't have it export everything, because Excel can actually not deal with the number of columns it actually puts out. It goes past ZZ. It has way too much data. So one of the primary goals of when we get this is to start paring down the data, to go through it systematically, step by step, looking at the data quality and getting to the point where we actually get data we can work with. So it's useful to do this way because usually people first, they want to jump and they want to look at what is the concentration of my sample. I try to discourage people from doing that, because until they've actually verified that the data is meaningful, that it's somewhat trustworthy data, at least from an analytical standpoint, there's no point in doing that, because you kind of get your own biases in there and your preconceptions. So I'm going to talk about each of these, but this is the raw relative standard deviation on Scandium, which is one of our internal standard elements. I'll explain why we're doing that. We then have a series of columns that are external calibration average. So what this means is this is the concentration in ppb of the different elements or isotopes of different elements that are listed here. So this is going to go through, it's going to list every element that we measured, and we can keep going out. And eventually we get to another section. This is external calibration quality control recovery percentage. So I'm going to jump back to the first, and first thing I'm going to do is I'm actually going to insert 5 lines here. And then I'm going to go here and I'm going to freeze my panes so that I can see what's going on. So I can jump to the end of this line. And now I can see that, okay, this recovery percentage is always occurring with what is our check standard here, Leonard 4. So this says that this is saying is that when it measured lithium 6, it measured it as 97% of the value we told it was. And so we're going to have all these columns of recovery percentage for our check standards. And so you can see there's lots of empty lines because that's only one check standard. And we also had, sorry, I skipped it across. So we have recovery percentage, and then we have recovery amount. So this is as a percent of the known, and this is in parts per billion. So it tells you that up here, it tells you what the units are. So this is, so we got 96% or 97%, and the concentration that we measured was 7.82 ppb. Okay, so our check standards and our standards in general are essentially designed to be similar to our samples. We do this so that a lot of the major elements are higher concentrations and trace elements are at lower concentrations. This is kind of a bigger discussion, but it helps when we're looking at interferences. It gives us more confidence in particular sample types. So some of these are going to be much higher than others. So we have more aluminum, a bit more calcium, and we have less of, say, strontium, or like the rare earth elements are sometimes much lower. We then have external calibration, limit of detection. So you can see this is the same number for the entire calibration curve, and this is in parts per billion. And what this is saying is that the limit of detection, or the amount at which you can statistically say with 95% confidence that you see something more than the blank, is at this concentration, or about 3.7 parts per trillion for lithium. And it's going to differ depending on which isotope you're looking at, because each isotope has its own calibration curve. And so these are going to be the limits of detection. And then we get over here and we get to external calibration, background equivalent concentration. And this is the number of parts per billion that is equivalent for the blank. And we'll talk a little bit more about that. And in this case, it would be 3.76 parts per trillion for lithium. So we're usually reporting several different quality control criteria about the low end of the calibration curve. We report limit of detection, limit of quantitation, and background equivalent concentration. So limit of detection we've already talked about. That's essentially, it's 3 standard deviations of the blank. It's essentially you measure the blank 10 times, and what is the noise on that blank? Is it noisy or is it fairly steady? And so then limit of quantitation is 10 standard deviations of the blank measured 10 times. So limit of detection is where we can say with some confidence something's there or something is not there above the blank. Limit of quantitation is the point at which we can actually start ascribing a value to that number. So you can have something that's above the limit of quantitation, but it might be off by 1,000%. Because if you're between the limit of detection and limit of quantitation, you really have very poor control over what error is there. You know something's there, but you don't have a good sense for how much is there. So I prefer not reporting values if they're below the limit of quantitation. And our older equipment actually used to be really nice. It used to give you a calibration curve, and it used to show you exactly what the anticipated error at various points on the calibration curve. And that was really nice for illustration, but we can talk more about that another time. So we have background equivalent concentration. So instead of the noise on the blank, this is now how high the blank is. So you take the number of counts per second you have at the blank, and you divide by the sensitivity, which is the number of counts per second per ppb. So that's essentially saying how high is the blank. And so for some things like sodium, let's see. Sodium, you can see we actually have kind of a high background equivalent concentration. What this means is the background is high, but it could still be have very little noise. So your limit of detection might not be bad. But so basically think of limited detection as the noise on the blank. Background equivalent concentration is how large the blank is. And that's it. So the first thing is you can see that this entire thing they put out has like all these columns. It's not very user-friendly. So one of the first things I'm going to do is take the spreadsheet and start turning it into something more workable. So for now, I'm going to forget about the external calibration, the check standards. We're going to get to those later. But I'm going to go out to where it starts listing the limit of detection. So I'm going to copy this. Actually, it's both the limit of detection and background equivalent concentration. I'm going to copy this. And I'm going to go ahead and I'm going to paste that here. Notice that I'm not pasting it in the first column because this is the relative standard deviation on one of our internal standard elements. We'll talk about that more later. So I start pasting it at lithium. I go out to here, and now this should be the beginning of the background equivalent concentrations for all of those. So I'm going to cut those and I'm going to put them on this line here. Then I'm going to go out here and I should check. I shouldn't have any cells that are filled here. So I'm basically doing some shortcuts because I've done this enough. But I want to make sure that all my things line up, because if you get off a column, it's going to really mess you up later. So now I'm going to say this is limit of detection and this is background equivalent concentration. So one of the first things I'm going to do is say, okay, I'm going to put in limit of quantitation here. So I know this is limit of detection is 3 sigma and limit of quantitation is 10 sigma. So I'm going to say this is 10/3 of the limit of detection. Oops, sorry. Okay. And now I'm going to paste this across. We're going to have some things where we have internal standard elements, and I'll talk a little bit more about that. Okay. So you can see this is the row in which we see what our units are. So most of the time we have parts per billion, but we have a few things here where they're percent. When they're percent, that means it's an internal standard element. So you can see here, we have actually scanned him twice because we were actually measuring in 2 different modes. If you're used to ICP OES, this would be like I was doing both axial and radial mode. In this case, it was to do with CCT, and we're not going to discuss that today. But we have scandium, we have germanium, we have yttrium, we have indium, and we have bismuth. So this is our normal suite of internal standard elements. The other thing I'm going to do is, so these are all to do with the bottom of the calibration curve. I'm then going to put in what is my top standard. And the reason I'm going to do this is because I'm going to start manipulating and cutting and pasting data later on. And I want to remember one of the primary quality control things I want to know is, are my samples actually on my calibration curve? Or were they at the very low end? Or were they going to be off the top of the calibration curve? So these 3 tell me about the low end. Now I have to say something about the high end. So I'm just going to take my top standard and I'm just going to paste that in there. And I'm going to keep going like this. Okay.
Gwen,
right.
Is it okay if we ask questions during,
Please,
or would you
please
rather?
do. Nope, please
Okay.
ask questions along.
I just have a brief question.
Yes.
In certain cases, so this is before the stage you're demoing right now, but let's say you had looked at the data before you exported it into the XLSX, and for one element and one calibration curve, you decided to omit the top standard for that specific element, maybe because it switched into analog mode or something. I'm not quite sure when and why this happens, but if you were to do that, does this mean that in the stage you're discussing right now, you would have to, for certain lines, be careful about what you chose as the top standard, or is
exactly?
I'm not asking a question quite
no,
right.
you're
you know
asking
what I mean?
it very, very clearly. So there are a number of cases we do this. Let's say that most of our samples were all between a couple of the calibration standards. It may not be as relevant to have the top standard. And we can talk, actually, it would be useful to talk at another time about why you might exclude the top standard. Another case would be, and Aaron knows this very well, is you might have multiple calibration standards because not all of the standard solutions were stable. And so I could have Sheldon here, and then I might have a platinum group element standard following it. And so in that case, I'd want to be sure that I was copying for the platinum group elements, I was copying the top standard for platinum group elements. So
Okay,
that's a great
yeah.
question.
Thanks.
All right, so the next thing I'm going to do is I'm going to leave this alone, and I'm going to basically copy this spreadsheet to a new tab. So I like to basically create tabs, and I want to keep things as transparent as possible. So this first tab, I'm going to leave all of my equations written in there. And so that way somebody can easily go back and see which top standard I was calling it. Because I could, because it's easy to make mistakes, and that way it can be traced. But now, from this point on, I'm going to start sorting things. And for instance, I don't want, if I sort this calibration curve or sort in lines, I don't want to lose this information. So I'm now going to copy this, and I'm going to paste as values. And that way, if I move the lines below, it's okay. I'm then going to rename this internal standard. And the first thing I'm going to do is I'm actually going to move and copy this again. And this one is going to be called standard. So each step, I'm doing one stage of the quality control process. So in this first one, I have internal standard. So what I'm going to do is I'm going to delete everything that is not an internal standard. So that means I'm going to delete this stuff. I'm going to delete this stuff. And I'm going to be left with only the internal standard elements. I'm going to delete everything that's out there. We don't care about that. All right. So what this is now is showing us what the recovery is through the sequence. So if there's a lot of deviations, so essentially what internal standard is doing is we're always having a little t, and we're aspirating the internal standard with our sample, and any deviations in the counts per second for that internal standard element, we're assuming is due to the instrument changing in sensitivity. So this could happen for a number of reasons. It could happen, cones aren't conditioned, the samples have a lot of salts. It could be all kinds of reasons. And so we want to know that the instrument, we want to be able to correct for any changes in the instrument's behavior over time. So now I find that big tables of numbers are not so easy. So I'm going to take this column of numbers, and I'm going to insert a scatter chart. So, and what I tend to do when I'm doing things like this is I like to put titles on stuff, because otherwise I'm not going to remember what I did. So my vertical, this is going to be internal standard, which I'm abbreviating IS, and it's recovery in percent. My horizontal chart is going to be basically sample number or run number. And the other thing I'm going to do is I'm now going to select data. So this one I can see is actually 45 scandium in KED mode. So I'm actually going to copy this column of data. I know it goes between D10 and D45. And now I'm going to add one, and I'm going to paste there and just make it the next column over. Copy again, next column over, so that's F. 72 germanium. And next is going to be G. 89 yttrium, KED.
Gwen, I might have a question once you finish this.
Go ahead and ask now.
Maybe maybe there's a specific reason you do this way. I know that if you, for the scatter plot type you have, you could also have selected cell D3. And then if you click the graph, you can just slide the whole group over and it will apply basically what you're doing, it will automatically do. But first finish what you're doing, and then I want to see, because there might be a good reason why you do it this way.
It might also not be.
It's
So
just a
I know
shortcut.
that you can do that, but I didn't know that you could duplicate the data that way.
So
right?
Can you do the first step again? Just make the graph of one. Yeah.
Okay.
It's almost identical to what you did. It's just maybe a shortcut.
I'm all about the shortcuts. Oops, no. So let me just do another one.
Yeah, add another scatter plot, the first column.
Okay.
I think you have to re-highlight the first column. Something went
Okay.
wrong with highlighting the column. Yeah. Sorry to interrupt. I'm hoping this helps everyone. So they're all different Excel tricks that each of us know, but none of us know all of them.
Okay, so I know if I go
here,
here, I can drag this and make it into another column, but I don't know how to duplicate it.
So put it back on the first column, and then you drag it back to the first column. So there's two things. I want to streamline adding the legend. So if you right-click the data point, any data point, and then go to data, select data, and then click on series 1, which is already selected, and say name. And then for name, click the cell D4.
Yeah, you can do that too. Yeah.
Okay. No, but there's more. So say OK now. And now what you can do, scroll to the bottom of your data and drag the right corner across through all 5 columns. And then when you put your legend on, the legend will include all of the data.
Nice.
Exactly what you did, but without typing them each in.
That's very convenient.
Just a shortcut.
Yeah, I appreciate that. That's excellent. I didn't know that you could do that. All right. That is a useful trick. Thank you.
So while we're waiting, what's considered like a out of acceptable percentage for internal standard recovery?
So that's a great question. It varies a bit, partly by instrument. So with our last ICP-MS, I didn't like to see anything fall, like 60% was getting pretty dicey. And I still would prefer to see things between, like a typical quality control you could institute is 20% more, so between 80 and 120%. But in actuality, it's often valid over a much larger range. So there's a couple things that I'm looking for. So A, I don't have a hard and fast rule on it, and I'll explain why in a minute. But ideally, I want it to be definitely greater than 50% and less than 150. That doesn't mean that data outside that is wrong, but so this particular ICP tends to have a lot larger variations in internal standard than previous instruments I've run. So had to learn that it's to be a little bit more flexible with that. So one of the things I'm going to do to judge whether I accept stuff kind of outside that value is keep a close eye on the check standards. If the check standards are behaving similarly to samples, meaning they have the same amount of internal standard suppression or enhancement, and they are still accurate, I may accept data outside that range. But definitely once you start getting below 50%, it's pretty problematic. There are cases where we have to do that. For instance, we had these recent cases with brines that they wanted to measure sub ppb parts per billion of manganese. And they were very problematic. And we had some real internal standard issues with that. But we finally got, by using a lot of secondary and certified standards, I think we got to values that are reasonable. So one thing to see here is that what I'm looking for when I'm looking at these, and I probably should have made them lines, but is I want to see that the internal standard elements are behaving consistently. So that means that I'm not seeing, like here, you can see, so it's actually really interesting. You can tell a lot about the samples. So first of all, we actually have this sample here, which is 0.33. And we can see at that point, all of a sudden the bismuth takes a dip, the indium takes a dip, and the scandium goes up. So if we go and look at 0.33, we can look at this, and I actually know about this sample. It actually has a very high ionic strength. It's got a lot of potassium in it and a lot of elements. And so a really common thing is if you have a high ionic strength, particularly for ICP-MS, you'll tend to see suppression of the internal standard. And one of the big reasons that we don't use only a single internal standard is that they don't always behave consistently. So some people will only use indium. But you can see here, like if I only use indium, well, at this point, scandium and things in the lighter end are behaving 30% differently. So that means if I'm trying to evaluate, say, lithium by using indium for correction, I'm going to be wrong by 30%. And sometimes it can be even more than that. Sometimes it behaves well. So all through here, you can see they're all about 100%, and they're all behaving reasonably consistently. But particularly when there starts to be a lot more enhancement or suppression of internal standard recovery, you'll tend to get you can get some real differences between how these are behaving. So this goes both as what the mass is and also has to do with the ionization potential and energy of those elements. So the instrument should be able to interpolate between, and we didn't discuss that today about how that would work, but yeah. So are there other questions about this?
I have lots of questions, but they get down in the weeds, and I think it shouldn't be included in this. But this is really nice. I think this is a good overview for everyone, and I'm really glad you're recording it because might be a nice way to introduce newcomers without having to every time reinvent the wheel. So thanks for doing this.
Sure. And actually, the other thing, though, that I forgot is about why do we have this column? And that is because this is a monitor. So this is basically the counts per second that we're measuring at 45 scandium, and it's the relative standard deviation. So let's think a little bit about what this means. We pick an internal standard element because we know we should always have a big signal for that. So there should always be a big signal. So it's not like we're looking at a blank where you can look at small deviations, might be like 45% on the blank, but that's okay because you have no counts. And so what this is a monitor of is if you've run out of sample, let's say either you've run out of sample or you've screwed up your timings, and so you aren't taking up sample, you'll tend to see bubbles go through the lines because you'll be taking an internal standard and sample, and now I've got no sample, and so I've got bubbles. And so this will be highly variable. So this is a quick monitor to see, to make sure that I didn't run out of sample. Because the instrument's not going to tell you that. It's going to measure everything 3 times, but otherwise you're not going to get a good indication of if you're actually taking in sample or not. So this is really a bubble monitor. And sometimes I'll put the error on here, but if it's all below 2%, I'm good. And okay, we have it slightly above 2%. That's okay too.
Could you very briefly, Gwen, just in the same way you did just before, if you click your graph and then just shift the data that's selected, so that not a data point, but the whole graph. Yeah, sorry, when it highlights the whole block. Nope, sorry. Yeah. So if you click on the gridded area and not the actual data.
Okay.
So that it highlight, in the middle of a grid, so it highlights all the data.
Okay.
And then shift it so it adds the first column, column C, and then we'll right click and we'll put that on the secondary axes. I'm just curious at a first order how that relates to the scatter in this data. So if you shift the blue selected data over, and then same way you did before, and so that it includes all the columns.
See. Yeah, hold on.
Sorry, this may or may not be interesting. I'm just curious. I probably should just play on my own instead of taking everybody's time. But and then if you right click that blue line and say on secondary, select yes, format data series and second axis. No, and it does not do anything like I thought it might, but I was just curious. Okay.
So typically
I thought it might somehow correlate with that.
No, typically, because it really is a pretty good monitor of bubbles.
Okay.
So I think otherwise it's pretty much noise. Now, if you had extreme suppression, so let's say I was suppressing my signal to like 20% of what it usually is, then you might see less variation, and so maybe it would be a tighter variation. But yeah.
So when you get the LOD data originally, is that the instrument measuring the blank 10 times, or is that something that you guys set from? Oh, okay.
So when we set up the run, I set up the run, and you can say I want a survey run, which is a real quick scan through the entire periodic table, and then you also want a main run, which is where you're actually sitting on it. You're systematically sitting on each of the elements of interest or isotopes of interest and measuring it. And you can say I want to measure one time. Usually we do 3 measurements, but for the blank I always make sure it's 10 measurements. But the instrument will actually give you an LOD even if you only had 1 measurement. And that, honestly, I'm not quite sure how it calculates that. So, but if you actually have 10 measurements and then do the calculation yourself, you'll see it does it correctly. Does that answer that?
Yeah, I was just thinking about, the Agilent OES and how we would potentially do that there, and if it makes sense to just start a run with like 3 to 10 blanks every time, or what. But
it doesn't, like, especially with the Agilent, it doesn't take much time. So I would suggest, because I'm not sure how it's calculating LOD otherwise, unless it's, it's underneath measuring the standard deviation of, that it's got multiple measurements, right? It's like what we have for 1 main run may be 100 measurements. So I think the Agilent's kind of similar, is it's got multiple reads, right?
Yeah, it does it in triplicate for one data point.
Yeah. Okay, so the main thing is here, I look at this and I see that things are mainly behaving together. There's some things that are behaving, that there's a little bit of variation, but it's kind of consistent so that like, okay, and this is very common too, that the lighter elements will tend to be either enhanced or suppressed much more than the heavier elements. They tend to just be more variable. So I'm satisfied. I think this passes all my quality control. So yes, it's got 40% recovery for some of these things, but that's on some of these samples, which I knew were going to be kind of problematic. We were talking about, these are Jamie samples, by the way, Sarah. So now I've kind of decided I've passed the internal standards. So I'm going to go on to the next step. And so what I'm going to do is kind of not think about the internal standards now, because I just have too much data to think about. So I'm going to go to this page that I copied, and I'm now going to delete all the internal standard elements. Just because I am got so much data, I can't think through it. So I'm trying to make it simple. All right. Oops. And just to clean things up, I'm also going to delete all these LOD and BEC lines because I've already got them copied in. Save. Okay. So now I want to start. Again, I haven't looked at all really at my data, at my sample data. I'm still looking at standards. So what I'm going to do is from about right here, I'm going to insert a line because this is my calibration curve and my blank check. Then from here on, I'm going to highlight everything, and now I'm going to sort by the name of the sample. And what I'm going to get is, okay, here I've got Leonard 4, which is my check standard. So I'm going to put that up here. And I have rinses. I'll just stick those here. And then I've got this other stuff. Now I actually have several different user samples in this particular run. But what I'm going to do now is I am going to copy this and call this one samples. And from this one, I'm deleting all my standards. But now I'm going back to the standards and I'm deleting all my samples. So I'm just looking at kind of quality from this standpoint. All right, so here I have my check standard. Oops, sorry. It's decided to pop up. Ugh, okay, fine, go away. Different thing. So here we go. Okay, something is odd is going on with my computer. Right, here we go. So I'll calculate what the average is here. Standard deviation. And I'll calculate what this is as a percent of the average. All right. And I'm gonna go across all my elements. All right. So what I'm going to look for is, ideally, I want my reproducibility on here to be less than 5%. Occasionally it might be a little bit more, like this phosphorus. And you can see here, this potassium, I'm a little bit higher. And one thing I'm starting to notice is, so here, let's see, so both phosphorus and potassium, and just a tiny bit, the calcium are a little bit high here. And I look across, okay, so, and the tungsten is low here. So actually, I'm a little bit curious about this phosphorus and potassium. So this is sequence line number 35. I'm going to go back to the test. What was run right before my 35? Oh, it was the mannitol stock. Okay, but it didn't actually have all that much potassium or anything else. But one of the first things, if I see that there's an elevation, I look to see, could the sample ahead of that one actually have been having some memory or bleed through? But this is generally okay. So now what I'm going to do is, that is the measured values. But remember, we also had basically these recovery percentages. So I'm going to go here and copy those recovery percentages. And then these, you can see, are all the same, and that's because these are the known amount for our check standard. So I'm actually going to put that right here and then throw in a couple of lines so that it will be a little clearer. Okay. So then standard deviation in percent. This is not really, doesn't really make, say, standard deviation, but it tells you, I'll explain what it means in a minute. And I'm now going to also just delete all this stuff because I don't need it anymore. First few times you do this, though, you spend more time checking that you've got all your columns lined up. I'm only doing this quickly because I've done it enough and I know I'm not going to screw up my columns. But I'm also always checking to make sure I have the right number of columns where I expect them to be and that kind of thing. So I'm going to put known value here. So this is going to tell you about reproducibility. And this is going to tell you about precision, right? So we knew that it was reproducible. Now we can look here for precision. So really, ICP-MS data is at best good to 5 to 10%. And actually, sometimes that's good to kind of like clarify with users. I've had people who expect it to give you precision of 0.5%, and it's just not possible. Unless you do like something weird like isotope dilution. So it's good to sometimes just clarify with users what their expectations and needs are. And sometimes you can tell it by the type of project, but sometimes users are not always, they're not sophisticated in understanding what the capabilities and limitations of instrumentation are. So sometimes it's our job to educate them. So I look here and I see, most of my elements are, they're reasonably accurate and they're also reasonably precise. I mean, I have a couple things that are off here. So zinc is a little high. I'm not surprised. Zinc is notorious for being in blanks and everything. If you want to do an experiment, and you can do this with ICP OES because it'll show up, take the finger of your glove, stick it into a 2% nitric solution and measure the zinc on the surface of your glove. You'll be shocked. So I'm looking across, and again, if the user wanted something specific, but you can see that there's a few things like, okay, here I'm 80% accurate with tungsten. Tungsten can be a little bit difficult sometimes, but in most things I'm like 5 to 10%. So far I'm saying the instrument, right now, everything has been up to the instrument is performing well. So now, after I finished all of that, then I go to the samples. And now I can look at the samples. And in this case, and it's common, I will actually duplicate this. And I'll make a separate sheet for each user because they don't need to see each other's data. I'm not going to go to the trouble of like deleting files, but so this is this was, oh yeah, this was Collins data. And this was data. Okay. So then it depends where I go from here, depends on the user. If the user is sophisticated, I just hand this off to them. If the user is not sophisticated and we've had to do sample prep, we're then going to do some more on data reduction on like including the dilution factor and things like that. But I think that will actually save for another time because everybody's been on Zoom for 2 hours now and they're all exhausted from Zoom. So